Our goal is analyzing this series. You have ln of 1 plus 1 over n, as n starts from 1, goes to infinity. Let us take the limit of this series. Let's see, what do we have? Remind yourself of the theorem. The theorem says if series an start from 1 goes to infinity is a convergent series, then the limit of general term as n goes to infinity must be 0. From this theorem, we defined a test. The test says if the limit of an as n goes to infinity is not 0, then the series is divergent. And start from 1 to infinity is divergent. Very well. So let us take a look at the general term here. This is my general term, an. If I take the limit of an as n goes to infinity, I'm taking the limit of ln of 1 plus 1 over n as n goes to infinity. ln is continuous, so you can write this guy as the ln of the limit. So limit goes inside of ln 1 plus 1 over n as n goes to infinity. So you end up with ln of limit of 1 plus 1 over n, but 1 over n as n goes to infinity is 0. You end up with 1 inside parentheses. ln of 1 is equal to 0. Okay. I found the general term to be limit of the general term to be 0. So the question is, it's a common mistake on exam. Common mistake on the exam. Student write, hey, since the limit of the general term as n goes to infinity is equal to 0, so we can conclude that the series of n start from 1 goes to infinity is a convergent series. Guys, this is wrong. It doesn't guarantee that you have a convergent series. Take a look at the terms of this partial sum. Let us write the partial sum. Here, what do we have? We know that Sn is equal to the summation of a sub I starts from 1, goes to n. We know that if the partial sum as a sequence is convergent, then the series is convergent. But take a look at your S of n. S of n is the summation. Let's go up. And here you have ln of 1 plus 1 over n. And instead of n, since we're using partial sum, let's use I. And I starts from 1, goes to n. So if you plug in values here, what do you get? If I is equal to 1, you get ln of 1 plus 1 over 1. If I is equal to 2, what do we get? We get ln of 1 plus a half, plus if I is equal to 3, you get ln of 1 plus a third, and continue this process. But take a look at this sum. You have ln of 2 plus ln of 3 over 2 plus ln of 4 over 3 plus the rest of the terms, am I right? So if you break this guy down into smaller pieces, you get ln of 2 plus, this guy can be written as ln of 3 minus ln of 2. This guy can be written as plus ln of 4 minus ln of 3 plus, if you continue this process, plus ln of 1 plus 1 over n plus the rest of the terms. And this guy is ln of n plus 1 minus ln of n. Behavior is similar to a telescoping series. What's happening here? Guys, I can cancel out ln of 2, negative ln of 2, ln of 3, negative ln of 3. I can cancel out negative ln of n and the term which is here, which is going to be ln of n. So what's happening here? I end up with ln of n plus 1. So this partial sum is nothing but ln of n plus 1. But the limit of Sn as n goes to infinity is the limit of ln of n plus 1 as n goes to infinity, which is infinity. So the limit of the partial sum is not a unique numerical value. So since the limit of the partial sum is not a unique numerical value, it means that the series of ln of 1 plus 1 over n and starts from 1 goes to infinity is divergent. Let us summarize this. Take a look at the steps that we took. Our goal is to analyze the following series. We have ln of 1 plus 1 over n and starts from 1, goes to infinity. The theorem that we learned saying that if a series is convergent, then the limit of the general term is equal to 0. From that theorem, from the contrapositive of the theorem, we took a test. The test says if the limit of the general term is not 0, then the series is divergent. So we took the limit of the general term. The limit of the general term is equal to 0. What's the meaning of that? We reach to a common mistake on the exam that students say, hey, since the limit of the general term is equal to 0, so the series is convergent series, which is absolutely wrong. Be careful here. So what are we going to do now? Since the limit of the general term is equal to 0, we need to check the series itself. We need to write the partial sum of the series and analyze that. The partial sum is defined as the summation of ai's, I start from 1, goes to n, Sn in terms can be written as ln of 1 plus 1 over I starts from 1, goes to n, and here you end up with ln of 1 plus 1 over 1 when I is equal to 1. When I is equal to 2, you get ln of 1 plus a half. When I is equal to 3, you get ln of 1 plus a third, and so on. You don't continue this indefinitely. You have to stop at ln of 1 plus 1 over n. This happens when I is equal to n. This is your last term that you're going to have. So ln of 1 plus 1 over 1 is ln of 2. ln of 1 plus a half is ln of 3 halves, ln of 1 plus a third is ln of 4 thirds. You can take the common denominator down here, and you have ln of, let me write this guy down for you here as ln of n plus 1 divided by n, as we took the common denominator over there. So now using the behavior of ln and its properties, remember that ln of a minus ln of b is ln of a divided by b. So as long as you have the division, you get ln of a minus ln of b. That's how we broke up ln of 3 halves into ln of 3 minus ln of 2, ln of 4 thirds to ln of 4 minus ln of 3, and ln of n plus 1 divided by n to ln of n plus 1 minus ln of n. But see the pattern, you have some opposite terms. ln of 2, negative ln of 2, they get canceled out. ln of negative ln of 3 and negative ln of 3, they get canceled out, and so on. You're left with just one term. This is ln of n plus 1 that is left, right? So you get Sn, which is the partial sum, to be ln of n plus 1. But if you take the limit of the Sn, it's the limit of ln of n plus 1, n goes to infinity, ln goes to infinity. What's the meaning of that? Based on the definition of convergence of a series, since the limit of the partial sum is not a unique numerical value, it means that the series itself is a divergent series.